And yes, there are some part of thermodynamics also from where question can be asked. So there are these two things that you'd be learning here. One is thermodynamics and the chemistry.
Yes, sir.
The physical part that you'd learn and the thermochemistry.
Yes, sir.
Now in thermodynamics, the meaning of thermodynamic is the transfer of heat, the study of transfer of energy by any means possible. Okay, Dinesh?
Okay, sir.
How many means, how many ways are there with which you can actually transfer energy? Majorly two ways are there, Dinesh. You can do some work, okay, or you
Okay,
can
sir.
pass on heat. This is how you can actually transfer energy. So the study of these things majorly will be done in thermodynamics.
Yes, sir.
Okay,
Yes, sir.
so this will be our concern in the chapter. Moving up with it, to understand about this thermodynamical things or these things that you'd learn in this chapter,
Yes, sir.
what you need to know or what you need to learn here is about this. So let us start with the basics of what are you going to use in this and what are you going to get to benefit of it. Like let's say if you know the thermodynamics, you'd be able to know how fast the reaction will happen, which direction. No, it will tell you which direction will the reaction will go to, which product will the reaction form, to what extent will the reaction happen. Okay, Dinesh.
Okay, sir. Sir,
Yes.
sir, in the chemical kinetics chapter, they told sometimes thermodynamics you can't use, so the finding the rate, so we are using chemical kinetics.
Yes. Majorly, the rate would be observed with kinetics. But which direction the reaction will go, what will be the effect, to what extent will the reaction happen, that would be learned and understood in this chapter, Dinesh.
Yes, sir.
So kinetics is to understand at what rate will it happen, right? At what speed it will happen.
Yes,
Maybe
sir.
I would have told that by mistake. In this chapter, you'd learn to what extent, to what direction. Okay?
Yes, sir.
Good. So this thermodynamics you can understand by understanding about the basic terminology that you'd be coming across. So in thermodynamics, you take the whole universe to be our concern. Okay, so
Surrounding.
everything around us is the universe. Okay,
Yes, sir.
Dinesh. Now this universe have two parts, Dinesh. You'd be working on some part of the universe, and that part where you'd be working on, where you'd be observing the process, is what we call a system. Okay,
Okay,
and
sir.
the rest of the thing is what we call a surrounding. Now what part is system? The part of universe where you're doing or understanding the process of transfer of energy is what we call as system. Okay,
Yes, sir.
this is that part of universe where changes are occurring, changes of energy or heat transfer is occurring. Okay, while
Yes, sir.
surrounding is rest. Come, I mean, apart from the system, whatever else is surrounding, everything else apart from the universe, apart from the system, is surrounding. Okay,
Yes, sir.
good. Now to separate this system and surrounding, you have something that we call as
Boundary.
boundary. A boundary can be of two types, Dinesh.
Imaginary and real.
Real, very good. Imaginary or real. I don't need to explain about this more, right?
Yes, sir.
Imaginary boundary, like when you have multiple gases present. So there is no boundary to define the gas, right? To confine the gas, right?
Yes, sir.
There's another way of classification that I need to tell you properly. That is diathermic boundary and adiabatic boundary. Diathermic boundary and adiabatic boundary.
Sir, this come under real, sir.
Yes, Danish.
Yes, sir.
Or you can take them to be a separate classification.
Yes, sir.
Or obviously, real only, adiabatic boundary. You don't need to be properly learning these two things. Nobody, no help it will do for you.
Yes,
Okay.
sir.
So majorly what you need to be understanding is adiabatic and diathermic boundary. Diathermic boundaries are those that allows energy transfer to occur only. Okay, Danish.
Yes, sir.
but it will not allow mass transfer. But anyway, this will allow the energy transfer to occur.
Not mass transfer, sir.
Not mass transfer. The other one is adiabatic bonding. Like you have seen a thermos, right? Thermoflask,
Yes, sir. Hot water.
hot water, cool water, tea, coffee,
Yes, sir.
that compartment, this compartment which does not allow heat or mass transfer to occur, such a compartment is called as thermoflask, or that kind of container or boundary will be called as adiabatic boundary. Okay,
Yes, sir.
so no mass or energy exchange occurs. Okay, Dinesh.
Okay, sir.
So this is what we call as adiabatic boundary.
Yes, sir.
Shall we move? Yes.
Yes, sir. Written, sir.
Hmm. Now let us further understand about the things that you'd be using when you'd be learning about this thermodynamics, Dinesh. You'd be learning or you'd be using systems. Like the systems which I've taught you, right? The systems can be of multiple types.
Isolated system.
Three major types of systems are there. Okay.
Yes, sir.
Actually, there are two types based on their constituents. That also I'll teach you in some time. We'll first understand based on the nature, based on the type it is. Okay, Dinesh.
Yes, sir.
So based on the type, this
Open.
boundaries, hmm, open system. Now, open system is like you are trying to boil some water, Dinesh. Okay,
Yes. Okay, sir.
you're trying to boil some water, and if you're trying to boil some water, what will happen, Dinesh? The water that you have in the container will start getting heated up, right or not?
Yes, sir.
Slowly and slowly, it will start getting heated up. And in this process, you're exchanging two things, Dinesh. What are these two things? One is you're transferring heat, you're transferring energy, right?
Yes, sir.
The second thing is from this, what is happening? The
Evaporation.
vapors, the evaporation would be constantly occurring there, right?
Yes,
So
sir.
exchange of mass also would be occurring constantly, right?
Yes, sir. So both heat and mass are getting exchanged, sir.
Yes, yes. So mass transfer and heat transfer or energy transfer both occurs. Better to call it energy transfer. Okay, Dinesh.
Okay. Yes, sir.
Any doubt in this?
No, sir. Both mass and energy are getting transferred, sir.
Exactly. Okay, both mass and energy will be getting transferred in this process, Dinesh.
Okay,
Fine.
sir. Fine, sir.
So in this case, the change in mass, will it be zero or it won't be zero?
Sir, it won't be zero, sir.
Very good. How about the change in energy, Dinesh? Will it be zero or it won't be zero?
Sir, entire system or beaker alone, sir.
What, Dinesh?
Sir, entire system or in the beaker alone, sir.
What is entire system, Dinesh?
Sir, including the burner, sir.
Not including the burner, just the beaker, Dinesh.
Sir, it will increase, sir.
Very good. And if you consider, I mean, that is what is happening. There is an exchange of heat that is being occurring from the system, from the surrounding to the container, right, Dinesh?
Yes,
So
sir.
our system is this beaker containing this substance. So let us move to the second kind of system, Dinesh.
Yes, sir.
Second system is closed system.
Only energy is getting.
Now this time you are trying to cook maybe something in a closed container, Dinesh. Maybe you're trying to use some cooker or something. Okay,
Yes, sir.
so you're trying to use a closed container because you're trying to use a closed container. If you try to use the same kind of heater, burner, or gas or whatever, this time when you try to heat it, what do you expect to happen? Would you see any mass transfer occurring here?
No,
Would
sir.
there be a mass transfer occurring?
No,
Or,
sir.
or before mass transfer, would there be a heat or energy transfer occurring, Dinesh?
Yes, sir.
Yes, energy would get exchanged, right?
Yes, sir.
Very good. So the change in energy would definitely be there. It won't be zero, right?
Yes, sir.
So energy change won't be zero. How about mass exchange? Is it possible for this thing to get evaporated, Dinesh, or it won't be possible?
Sir, it's not possible, sir.
Very good. So change in mass will definitely be zero. Clear?
Clear, sir.
Good. So that's the point about the second kind of system, the closed system. Okay, Dinesh?
Okay, sir.
The third example or the third type of system is what we know as isolated system, Dinesh.
Sir, no mass or energy is getting.
Yes, yes, yes. That kind of system is what we call as isolated system. Just now I've given you an example of thermo flask, right, Dinesh?
Yes, sir.
Container which is completely adiabatic do not allow the mass transfer or energy transfer to occur. And because there is no mass exchange and no energy change, that kind of system will be called as an isolated system, Dinesh. Okay? No
Sir,
mass transfer or no energy exchange occurs.
yes, sir. Sir, this has adiabatic boundary, sir.
Yes, yes. Then only it will be possible, right, Dinesh?
Yes, sir.
So these are the types, Dinesh. In the first case, you have imaginary boundary. In the second case, you have real boundary. In the third case, you have diathermic real boundary. Okay, Dinesh?
Yes, sir.
Any doubt in this?
Sir, in
Mm-hmm.
second case, diathermic, sir.
Diathermic heat change is occurring, right?
Yes, sir. Third is adiabatic, sir. First one, sir.
Yes. First
No.
one is open imaginary system and an imaginary boundary.
Yes, sir.
Hmm. So you've understood about the types of system based on the kind of boundary they have.
Yes, sir.
Good. So let us move towards the next one. I mean, this system itself can be again understood or taken in these two types, Dinesh. The system can again be further divided into two systems or two types based on the constituents that they have. One is called as a homogeneous system,
Yes, sir.
and the other one is called as heterogeneous system. And what is homogeneous and what is heterogeneous system, Dinesh?
Sir, the composition is same throughout in homogeneous, sir. Heterogeneous, it varies, sir.
Exactly. Let us say if you have a reaction H2 plus O2 gives 2H2O, Dinesh. Or a better example, N2 plus O2 gives 2NO, although it is endothermic. In this reaction, everything is in gaseous state, right, Dinesh?
Yes, sir.
So the state, the phase, and the properties of these things will be very much similar to each other as they're all gases, right,
Yes, sir.
Dinesh? And
Right,
they
sir.
all would be having the same phase, uniform. On the other
Yes, sir.
hand, if you see a reaction like CaCO3 gives you CaO, okay, calcium oxide plus CO2. In this process, what is happening is you're getting two solid and one gases. So different substances have different nature, and the state also are completely different among them. So
Yes,
such
sir.
a system is what we call as heterogeneous system. When we'd be learning about thermochemistry, this classification would be of more help for us.
Yes, sir.
Okay,
Sir, this classification is mainly based on phase of the system, sir.
mainly based on the constituents, Dinesh.
Sir, all should be in same phase, then it's homogeneous, sir.
Homogeneous, exactly. If they're in different phases, heterogeneous.
Yes, sir.
Any doubt?
No, sir.
Yeah, finish. So after understanding about this heterogeneous and homogeneous system, let us move and try to understand about what are the other things that we know to understand the system. Or to understand the system, we would need certain characteristics, right, Dinesh?
Yes, sir.
You need certain properties, right or not?
Right, sir.
So what do we need to understand a system? To understand the system, we need characteristics. Okay, for example, you need variables, properties, or functions.
Yes, sir.
Different names are there, Dinesh. Okay,
Yes, sir.
and what these things are is a way in which the whole process actually occurs. Okay,
Okay, sir.
for example, you can have pressure, volume, work, enthalpy, internal energy, gives free energy, entropy, right, Dinesh?
Yes, sir.
These are all what we know as the properties, the functions, the variables. Okay, Dinesh?
Yes, sir.
Now, there are this variables or this functions depending upon their way of behavior. They are classified into two different types, Dinesh. Actually, one way of classification makes them extensive and intensive, and there is another way in which you'd call them state or path. So we'll first look at them being extensive and intensive properties.
Yes,
Okay,
sir. Okay,
these
sir.
functions or these properties can be extensive and intensive.
Yes, sir.
Extensive properties or functions.
Sir, intensive means it does not change, sir, and extensive changes, sir.
Very good, very good. I'll give you an example, Dinesh. I want to do party, but I'm just able to get to some thumbs up or some kind of cool drink. Okay, Dinesh.
Yes, sir.
And I've gone there with my friend. So both of us are standing. Now I've taken just one glass of this thumbs up. Okay.
Yes, sir.
Now both of us are going to actually share this thumbs up. Fine.
Yes, sir.
I've taken some amount of it. Okay, Dinesh.
Yes, sir.
Hello.
Hello?
Yes, yes, yes. So I've taken some amount of this thumbs up, and initially the volume would have been 200 or 300 milliliter, Dinesh, depending upon the total volume. Okay.
Okay, sir.
Now, after taking some of it, there'll be some amount of cool drink left, right, Dinesh?
Yes, sir.
So that part my friend will take, right or not?
Right, sir.
So if you consider the density, Dinesh, the density of that liquid inside that bottle, would it be same when I drink it and when my friend drink it? Will be different, Dinesh.
It will, same, sir.
Very good. So density remains same. Now, if you look at the volume, Dinesh,
Sir,
what do you think about the volume?
it changes, sir.
Yes, so volume changes with change in amount. So those properties that changes with a change in amount are called as extensive property. And those properties that stays the same even on changing the amount are called as intensive properties
Yes,
or
sir.
functions. Okay, Danish.
Yes, sir.
So we'll classify some of the things or some of the properties when we'll just write the names of this. For example, for extensive property, you have volume for just now, you've learned. Apart from volume, mass is also extensive, right, Dinesh? Number of moles, okay?
Okay, sir.
Moles, internal energy, energy. This depends on the amount. Um, okay, Dinesh.
Okay, sir.
Enthalpy, enthalpy gives free energy, entropy. These are all going to be dependent on the amount, Dinesh. Is that clear?
Yes, sir.
Good. On the other hand, if you look at intensive properties, all the molar values,
Sir, what is
all
GNS, sir?
G is gives free energy, Dinesh.
Yes, sir. Yes, sir. Okay. Yes, sir. Spontaneous.
S is entropy,
Entropy. Okay, sir.
measure of spontaneity, measure of disorderness.
Yes, sir.
You'll come across this very soon.
Yes, sir.
And like all the molar values, like molar volume, okay, it's a fixed value. Density and pressure, right, Dinesh?
Yes.
Boiling point, viscosity, and then mu, eta. Eta is viscosity, right?
Yes.
Mu, okay, mu is refractive index, I think, that you'll use in physics. All this, surface tension, refractive index, these are all the properties that we call as intensive properties, Dinesh. Boiling point, melting point, majorly boiling point. Okay,
Yes, sir.
so these are
Melting point, sir.
what, Dinesh?
Melting point or boiling point, sir?
Boiling point, boiling point.
Boiling. Okay, sir.
These are all intensive and extensive properties. Any doubt in intensive and extensive, Dinesh?
No, sir.
Yeah, you can copy it.
Yes, sir. Copy, sir.
Copy it.
Yes, sir.
The next thing that we need to understand is another way of defining these variables or systems, Dinesh. For example,
State and
yes, state and path function.
yes, sir.
Now let us say this time I've gone to the top of a tower with my enemy instead of my friend this time. Okay, Dinesh.
Okay, sir.
Now at the top of the tower, what will happen, Dinesh? What do you think? I mean, it's a very, I mean, it's not very high. The height is not very lot. So what we'll do is there are two ways, Dinesh. We have a stair, okay,
Yes, sir.
which you can do. We can do it go down, or I can just kick my friend, and by kicking him or her, what will happen? They will directly fall down to the ground, right, Dinesh?
Right, sir.
So in both the cases, he or she will reach to this point. But there are two ways in which he or she will reach there. One way is I can just kick her or him. Second
Yes, sir.
way is they can take the ladder or they can come down. With that ladder, they can come down, right?
Yes, sir.
In which case, would they be doing more work, Dinesh? Not me. Obviously, on kicking them, I would put some effort, right?
Yes, sir.
Now you tell me, in which case would they be putting more effort, or they be doing some work, or would in both the cases the work done is same?
Sir, displacement is same, sir. Force is different, sir.
Mhm. Displacement in this direction is same, right, Dinesh? In this
Yes, sir.
direction
Force
also,
force may be different, I think, sir.
yes, force will be different, so work done will be different, right, Dinesh?
Yes, sir.
In one case, I am applying the force. In other case, they are working to walk down the stairs, right?
Yes, sir.
So work is dependent on the path which they are trying to take in order to come down, right?
Yes, sir.
So such a function that depends on the path is what we call as path function. Those variables or those functions that depends on the way they would reach the final state, okay, are called as path functions.
Sir, work and heat, sir.
Work and heat, very good. Functions that depends on the path or the process used. Okay, Dinesh,
Yes, sir.
are called as state function. Apart from the state function, I mean, many examples of state functions are there. You can have work, right, Dinesh? What
Yes, sir.
else can be a state function? Oh, sorry, path function. What else can be path function, Dinesh? Work, heat, right?
Yes, sir.
Energy. I mean, these are the examples. Energy due to friction. These are the examples of path functions. What is the example of state function, Dinesh? That only depends on the initial and final state. It does not matter how you're going to achieve it. For example, the height. Ultimately, you're going to come to this height no matter what process you'd use, right, Dinesh?
Yes, sir.
You jump directly or you walk or take the stairs. Although you may die or not, that's a different scenario, a different case altogether.
Sir, but we
But
reach there, sir.
you'll reach there. Yes, the point is that. So state functions are those functions that depends
Yes, sir.
only on the initial and final state of a system. Initial and final state of a system.
Yes, sir.
That is what we call a state function. Can you give me some examples of state functions? Almost all these thermodynamic variables, Anish, are state functions. For example, Gibbs free energy, internal energy, entropy. Okay, Dinesh,
Yes, sir.
are examples of state functions. While heat is not, work is not, volume, pressure, these are all state functions, Dinesh. Any
Yes, sir.
doubt in this?
Volume, pressure, temperature, all are states, sir.
Yes, temperature you can increase in whatever way possible. Ultimately, T1 and T2 are going to be matter or going to be a matter of concern, right? So
Right,
all
sir.
the state functions, if you take, you'll be able to write U2 minus U1. You'll be write del G is equal to G2 minus G1. Okay, Dinesh. So these are
Okay,
all
sir.
additive. Any doubt in this, Dinesh?
No, no, sir.
Good. So now that you've understood about mm, the kind of functions that we have, we can directly dwell into the kind of processes that you would use in thermodynamics. Do you copy this?
Yes, sir. Isothermal, adiabatic.
Yes, yes. So let us move to the thermodynamic processes, the process that you'd have, or what is this process first of all? What is a process, Dinesh?
Sir, method to do the work, sir.
Yes, bringing a change in the variables of a system, bringing a change in the condition of the system
Yes, sir.
in the thermodynamic variables is a process. Okay.
Yes, sir.
So this process is in which is a way by which you make the changes in the variables of thermodynamics. So you completely define the system. You completely change the definition of system. It may be in a different state initially, and after doing the work or whatever thing that you're doing, it will reach to a different condition where the values of these functions or variables will all be different.
Yes,
Is
sir.
that clear, Dinesh? For example,
Sir,
you
this is the complete definition, sir.
bringing a change in the variable of a system.
After
How does
system.
it? Hmm.
Yes,
Now let us say if you're trying to look up a system and system is at point this, okay, then it's at point A where the pressure is P1, volume is V1. Now you've brought it to point B, Dinesh, where the pressure is P1 and volume is V2. Now you are bringing it to point C, Dinesh, where pressure is P3 and volume is V2, Dinesh. So from A to B to C, these are different processes, Dinesh.
yes, sir.
These three things are what we know as process. Okay.
Sir, last one is ABC, sir.
Last one is A, B, C. Okay, Dinesh.
Okay, sir.
Different types of process. If you look at AB, if you look at AB, you'd observe that
Yes, sir.
there is no change of pressure. Pressure remains constant throughout this process, right or not?
Right, sir.
So you can do a change, you can bring a process or you do a process, and by doing a process, you may keep the pressure constant. And if you look at the second process, Dinesh, you look at the second process,
Volume
you,
constant, sir.
the volume remains constant. So this process can be of different nature. Do you understand that?
Yes, sir.
ABC is a complete process. You can also have a process from A directly to C, Dinesh, in a way of a curve, in a hyperbola manner, Dinesh. In such a process, you would have temperature constant, Dinesh.
Sir, we can't have straight line, sir, from A to C.
If A to C is very near to each other, you can still have temperature constant, and you do make a straight line.
Sir, it's always hyperbola, sir.
If it is temperature is constant, it would behave like hyperbola, right, Dinesh? You have V inversely proportional to P, right? You remember ideal gas equation or Boyle's law
Yes, sir.
because of that.
Inversely proportional, sir. So it's coming like uh, curve, sir.
Yes, hyperbola.
Yes, sir.
Okay, Dinesh.
Okay, sir.
So this is what we know as process. There are different types of processes, Dinesh. Majorly, if you look at these types, Dinesh, they are divided into two types.
Yes, sir.
These two types of process that are being divided are reversible process and irreversible process, Dinesh. Irreversible and reversible process.
Yes, sir.
Irreversible and reversible process. Now, what do you think about this reversible and irreversible process? What
Sir,
would be different among them?
sir, reversible process take infinite time to complete, sir.
Very good. Only those processes which would take actually infinite amount of time to get completed are called as reversible process. That's one way of looking at it. Let's properly understand what a reversible and irreversible process is. We'll assume that we have a piston. You can have many other examples. I'm just choosing this.
Yes, sir.
So you have this piston, Dinesh,
Yes, sir.
and you've kept some gas inside it. And above this piston, you've made a big place and you've kept a very, very big stone. Okay, Dinesh,
Yes, sir.
maybe 1 ton. Okay, so very, very heavy stone
Yes, sir.
or iron slab,
Okay, sir.
very heavy. And you're Superman. Okay, so this time what you're going to do, I'll tell you in some time.
Yes, sir.
when you have superhuman strength. Okay. So what you're going to do is you're going to kick this stone all of a sudden. Internal pressure is P, and because of the stone, there'll be a outside force from constant force from outside, which we write as P external. I mean, which will generate a pressure, P external, Ganesh. Okay.
Okay, sir.
So this constant external pressure is being exerted on it due to this heavy stone or iron slab kept above it. And because of this pressure inside the gaseous container, they are like managed or they are stable at this position. Okay, Dinesh.
Okay, sir.
Now all of a sudden you've kicked this stone and you're capable of completely throwing it away from this place to maybe some other place. Okay, Dinesh.
Okay, sir.
Okay. And what happens when you kick it? All of a sudden, the pressure that is being there from the top of this, what do we call? This
The
piston
slab,
will become zero, right,
zero.
Dinesh? No,
Yes, sir.
not zero, or will become equal to the atmospheric pressure now,
Yes, sir.
right, Dinesh?
Right, sir.
So this slab, don't think where this slab will go, maybe on some place, okay?
Okay.
And this pressure that you now have will be open to the atmosphere. But the pressure that you have inside will still be same, Dinesh. Okay, the internal pressure will still remain same. It is still capable of holding this pressure. So if you come across this small value of pressure, what will happen to the piston? Will it stay in that place or it will rise to a certain level?
Sir, it will rise, sir.
Very good. And such a process is what we know as expansion. But in this process, do you think it would have taken a huge amount of time to happen, or just an instant to happen?
Sir, sir, I don't know, sir. Sir, it may take some time, sir.
You kick the stone, you kick the stone, all of a sudden there is no pressure on it, right, from outside,
Yes, sir.
right, Dinesh?
Yes, sir. It may
So
take
all of a
some
sudden
time.
it'll start moving up, or it will wait for somebody to make it, or to ask them to move up. It wouldn't wait for anybody to ask them to move up, right?
Sir,
To
but
ask it to move up, right?
depending on size of the gas molecules,
Always,
it will take some time, sir.
you have some internal pressure there, Dinesh, right?
Yes, sir.
And this internal pressure is capable of holding this to this level, right?
Yes, sir.
That means initially the internal pressure would have been equal to the external pressure that you had initially, right, Dinesh?
Yes, sir.
At this condition.
Yes,
So
sir.
all of a sudden, when the external pressure is brought down to this value, this would be many times more stronger than the external pressure, right, Dinesh?
Right, sir.
So what will it do? It will allow it to stay there, or it will completely move up because of high pressure inside the gas.
Sir, it will completely move up, sir.
And that will not take more than an instant. It occurs instantly. Is that clear?
Clear, sir.
Very good. And this process that has occurred instantly is going to be at the moment, and you don't need to put some external effort for that. Because of being so fast, the variables that you have there that defines them completely changes all of a sudden. And it cannot be reverted back in general. Such a process is what we call as irreversible reaction. Oh, sorry, irreversible process. Is that clear, Danish?
Sir, this one is for irreversible, sir.
Yes. This one is for irreversible process.
Sir, it
It
occurs
occurs
instant.
against a constant. Mhm.
Sir, the 2 points are it occurs instantly and
It
occurs.
occurs against a constant external pressure.
Sir, here the external pressure is atmospheric pressure, sir.
Yes, yes, yes. The pressure won't be variable, Dinesh.
Sir,
Okay.
it's always
Mhm.
pressure or it is some other.
Anything. I'm just giving you one example, Dinesh.
Okay, sir.
Okay.
Okay, sir.
Now, when it occurs, Dinesh, there will be heat exchange occurring. Okay. This process occurs. I mean, this irreversible process occurs. I mean, all of a sudden, I mean, in a very quick manner. Okay, Dinesh, this is actually a real thing that actually occurs. Other processes, I mean, irreversible process or reversible process is like imaginary, Dinesh. Well,
Yes,
irreversible processes are actually true. They occurs. Okay,
yes, sir.
they take a finite amount of time. It's a natural process. Okay,
Yes,
any
sir.
doubt in this, Dinesh?
No doubt, sir.
Good. Now let us move towards the reversible, Dinesh.
Yes, sir.
Let's say you have kicked the stone and the stone is crushed completely because you're Superman. Okay.
Yes, sir. Yes, sir.
Now this crushed stone has come above the container that you've kept in the other piston. So now it has become sand. You've kicked it so hard that it has completely converted to dust, Dinesh.
Sir, it's still there only, sir.
Still, it is there on the other container, but in the form of sand because it has got crushed so much. Okay, Dinesh, you have so much of power.
Okay, sir.
Now, because it is crushed completely, and we want to look at a reversible process, what we would do here in this process is this time you won't try, I mean, you won't be able to kick it anymore. What you would do now is you'd start hand picking each of these sand particles one by one, Dinesh.
Yes, sir.
Okay.
Okay, sir. So,
Now, by doing so, it will take infinite amount of time for you to completely take out the particles of sand, right?
yes, sir.
And in this case, P external will keep on decreasing from P external with a small value of pressure. As you have taken out some amount of sand particle, it keeps on decreasing with a small amount, Dinesh.
Yes,
Okay,
sir.
that's why this dP.
Yes, sir.
Because of this, the whole process would occur, but it would take infinite amount of time. Okay, Dinesh,
Okay, sir.
infinite amount of time. And when this process is occurring, at any moment of time, you have equilibrium present. I mean, it can move in either direction, Dinesh, at any moment of time. Okay.
Yes, sir. Okay, sir.
The whole process occurs via, I mean, by being at equilibrium. With equilibrium condition, at any moment of time, you can revert it back.
Yes, sir. Sir, P internal minus dP, sir.
Is this
Can't,
clear, Dinesh?
sir, P internal
Okay.
minus.
It is completely an imaginary process, Dinesh. You can't actually hand pick those one sand particles, right?
Yes, sir.
You were asking something?
Sir, it's P in external minus dP continuously, sir.
Yes, Dinesh. Yes. P external minus dP keeps on changing, Dinesh. You understand that?
Yes, sir.
Hmm. So this is what we actually call as the reversible and irreversible process, Dinesh. Any doubt in this?
No, sir.
No doubts, right? It's clear,
No,
right?
sir. Sir, can you zoom it, sir?
You've copied it, Dinesh?
Sir, can you zoom it, sir?
Yes, yes, yes. Is it visible now?
Sir, the second point, sir, process occurs with equilibrium.
Process occurs with equilibrium conditions, Dinesh.
Yes, sir. Yes, sir. Yes, sir.
It's an
Noted.
imaginary process. Copied?
Copy, sir.
Yeah. So let us move further and try to understand about the other processes. So this is one way of classifying the process, Dinesh. Okay.
Okay, sir.
The other way of classifying this process is based on based on the nature that I've told you in the graphs, Dinesh. First one. The first one is isothermal process. What do you think this kind of process would mean, Dinesh?
Sir, heat is constant, sir.
Yes, you've already looked at this in gaseous state chapter, right?
Yes, sir.
Constant temperature process. All this you would have studied in 11th standard, right? Properly.
Yes, sir.
Or this chapter you completely skipped. So
Sir, no, sir.
delta T would be equal to 0 here.
Okay, sir.
You've
The
studied.
uh, some concepts I'm facing difficulties, sir.
Okay, Dinesh. The next thing or the next process is isobaric process, Dinesh.
Constant
Iso
pressure.
means same. Yes, yes. Constant pressure process. In this process, the pressure is going to remain constant. So delta P would be equal to 0 here, Dinesh.
Okay, sir.
The third one, that we have is constant volume process, isochoric
Sorry.
process, Dinesh.
Yes, sir.
In this isochoric process,
Delta V equals
volume remains constant. Yes, delta V is equal to 0. Volume remains constant. And the last, not the last process, and the next process is adiabatic process, Dinesh. Adiabatic process.
delta H is equal to 0, sir.
Now, what do you think will happen? What, Dinesh?
Delta H is equal to 0, sir.
Delta H is equal to 0 or heat is equal to 0, Dinesh? Q is equal to 0 in this process, okay? No heat change would occur here. Is that clear, Dinesh?
Yes, sir.
No energy change from outside to the inside, okay?
Yes, sir. Sir, what is difference between
Can you hear
adiabatic
me,
and
Dinesh?
what is difference between adiabatic and isothermal, sir? Sir,
In isothermal, temperature remains constant. In
adi
isothermal,
yes, sir.
1 minute, Dinesh, let me just write it. In isothermal, temperature remains constant. Change does not occur. And here Q remains constant. So delta Q is going to be equal to 0. Well, delta T here won't be 0, Dinesh. This need not be true. For example, if you have an endothermic reaction, Dinesh, in this endothermic reaction, before the reaction happens, let's say temperature is T1, and after the reaction happens, the temperature will drop from T1, right?
Yes, sir.
Right or not, Dinesh?
It will drop, sir.
Hello?
Hello? Sir, yes, sir. It will drop, sir. Temperature will drop, sir.
Can you hear me, Dinesh?
Yes, sir.
So do you understand in this process, temperature change is occurring. In this process, temperature change is occurring inside the container. But do you think
Yes, sir.
heat transfer is occurring from inside the container to outside the container?
No, sir. Sir, can you hear me? Hello? Sir?
Hello, can you hear me, Dinesh? Hello, is my voice audible to you, Dinesh?
Yes, sir. Audible, sir. Audible, sir.
Maybe some issue was there.
Yes, sir. Sir, can you hear me, sir?
Whether you did not hear me,
Sir, I could hear you, sir. Could you hear me, sir?
were you able to hear me from the beginning, Dinesh? Did you hear about this? Yes, yes, you're audible now, Dinesh.
Sir, that in
Okay.
exothermic process, temperature is decreasing, sir, but heat is not leaving the container, sir.
No, it's not going out of the container. It is happening inside the container, but not with outside environment, right?
Yes, sir.
Right, Dinesh?
Right, sir.
No heat transfer, right? No
Yes,
heat
sir.
transfer occurs here. So that is what we call as the adiabatic process. But temperature change may not be zero here, Dinesh. Keep that in mind. That's the difference between adiabatic and isothermal process.
Yes, sir.
Otherwise, people would confuse as adiabatic to be isothermal process.
Yes, sir.
And there is the cyclic process, Dinesh. The cyclic process you'd learn more of in physics, okay?
Yes, sir.
Carnot cycle or the things you would have studied, right? Process that completely turns back from initial to again the initial state is called as a cyclic process, Dinesh. Everything remains same. I mean, whatever values would come out to be the same again. Okay, Dinesh?
Okay. Okay, sir.
Hello?
Hello, sir. Can you hear
Hello?
me?
Yes, Dinesh, what happened? You're able to hear me?
Yes, sir. Uh,
Am I audible to you?
yes, sir. You are audible, sir. Can you hear me, sir?
Yes, yes, now you're audible, Dinesh. So cyclic process is clear to you?
Sir, can you go before page, sir?
What, Dinesh?
Before page, sir.
Yes, yes. To this?
Yes, it does not.